algebra students. We're going to continue our lectures on roots and radicals, and we're going to continue with more on the operations with roots and radicals. Last video we did adding and subtracting radicals and simplifying them. So today we're going to tackle multiplying and dividing radicals and roots, and learn how to rationalize radicals and simplify them. So again, we want to remember our definition of square roots, cube roots, etc. and understand those rules and applying those to multiplying and dividing. So more roots, more fun with roots. Okay, to begin with, what we want to do is look at our main goals here. And I use a little short way of saying multiplication. We use a symbol, the X with the circle around it, to indicate multiplication. So our main goals is to multiply and simplify different roots. And we want to divide, do something called rationalize, and simplify when possible. Okay, so let's go ahead and start with our multiplication rules. So with multiplication, what we want to do, just a second, I have to get a better marker. There we go. With multiplication, what we want to be aware of is that the rules are we can only multiply radicals with the same index numbers. And as long as we have the same index number, the letter N is our symbol for index number, if you recall from a previous lecture. As long as those are the same, we can multiply what's inside the radicals, the radicands together, and we multiply the coefficients together. So to multiply our radicals, what we want to do is be sure that we know the rule. You can only with the same index number n. Okay, so you can only multiply square roots together, cube roots together, fourth roots together. And the other thing we want to do is we multiply the coefficients and multiply under the roots, the radicands. And then your last step is to simplify. So multiplying our radicals, these are our main steps. Okay, so let's apply these steps to an actual example problem. Let's go ahead and start with an example. Here's our examples. And these will be much in line with what you typically see on homework problems, worksheets, quizzes, exams, etc. So in these examples, we want to, the directions will be multiply and or simplify. Okay, sometimes the directions will say both or just one or the other, but you need to be aware that you want to do both. You always want to make sure you simplify radicals. Okay, so to start with, let's go ahead and just take a problem like this, where we have the square root of 3, and we're going to multiply by the square root of 5 plus 2 to begin with. Okay, so the first check is to make sure that when we're multiplying, we are allowed to multiply these together. So this radical is the same type as this radical, meaning that the index numbers are both the same. They're both square roots. Okay. So the way we go about doing this is we say, okay, we're going to multiply the square root of 3 times the square root of 5. So we're going to distribute this just like we would a regular problem. So the square root of 3 times the square root of 5, you can do those two. Add the same next number. Then we want to multiply the square root of 3 times this plus 2 here. Distribute it like we did before. So we're going to say plus the square root of 3 times 2. Okay, so what we do is if we have any coefficients, we multiply these coefficients. Okay, so this is just a 1 and a 1, understood 1, so nothing there to multiply, it's just 1. But then I just multiply what's underneath these root symbols and I get the square root of 15. And then in this case, what we tend to do is reverse the order. We like to write the coefficient out in front so this 2 doesn't get mixed up as being underneath the root. So the square root of 3 times 2, just a regular 2, there's no roots. What I do is just multiply that 2 with this coefficient and say 2 square roots of 3. Okay. Now my next step is to look at this, combining like terms if I need to, and also simplify, which means simplify any radicals, which means get as much out underneath the square root sign or any root sign as possible. In this case, the square root of 15, there's no perfect square numbers underneath that are factors of 15, so this is as simple as I could get with this statement. And that would be my final answer. Okay, let's step it up a little bit. Okay, I have some thought out examples here. Now let's go ahead and just change the same type of problem just a bit. And we're going to say the square root of 3 to square root of 5 plus 2. Okay, how is that going to change things? What we want to do here is see what happens when we add another coefficient here. Well, the same applies. We distribute when we multiply, so this becomes square root of 3 and square root of 5. I'll multiply these two parts together, so this becomes square root of 3 times 5, and I multiply what's in front of the coefficients, 1 times 2. Okay. Now I'm going to multiply the square root of 3 times 2 again, and that will be as done in the previous step. In this case, now I just have 2 square roots of 15 plus 2 square root of 3, and I look at this, so I see if there's any like terms I could combine. I see if there's any parts of the radicals I could simplify, and no to both those two questions in this case. Nothing can be simplified further, so this would be my final answer. Next step here, let me go ahead and add 2 square roots. Let's say we have 2 square root of 3 times, I'm going to do the square root of 6 plus square root of 2. I'm going to step it up a little bit here. All right, let's add a few more items. Follow the same rules. So again, distribute and use your multiplication rules and then simplify. That's the core idea in doing these. Okay. So taking it step by step here. Now, this item times this item. I look at the coefficients and I multiply this. This becomes 2 times 1. I look at the radicals, they're the same types, and I multiply those. This becomes square root of 3 times 6 underneath the square root side. Then on this next side, when I say this times this, I multiply the coefficients together, and then I multiply the radicands together, what's underneath the square root sign together. They are the same radical, so I'm allowed to do that. This becomes 3 times 2 underneath the square root. Now I'm going to go ahead and take a next step. This becomes 2 square roots of 18 plus 6 square roots of 6. And next I want to simplify each of these if I can. Okay, I look at the square root of 18, I say, okay, can I break that down any? Now 18, excuse me, has a factor that's a perfect square, and that's 9. We did that in a previous lesson. This becomes 9 times 2, in which the square root of 9 is equivalent to 3, so I bring that out. I make this 2 times 3 square root of 2. Okay, so 18 is not a perfect square, but it contains a factor that is a perfect square, which this part, the square root of 9, becomes 3, and I can move that into my coefficient. And that's a simpler radical to work with. Now the square root of 6, I wrote that down again because it has no factors that are perfect square. That is as far as I can go. So my final answer to all this will be 6 square roots of 2 plus 6 square roots of 6. And these are not the same, they're not like terms, so that is as far as I can go. But I multiplied and I simplified, and that is my final answer in this case. Okay, so next up, let's do some with x's in them and look at a FOIL method. So we can have all kinds of radicals thrown at us, as we know from previous exercises in simplifying. We can have x's and y's and inner radicands, etc. Okay. Here is another good example. Let's do 2 square roots of 6 times 2 square root of 5 plus square roots of x, plus the square root of x. Okay, same idea. Let's go ahead and multiply these. So we're going to distribute and then simplify. Okay, so first step here, we have 2 times 2 out in front. We have the same roots, so we can multiply the 6 times the 5, so that becomes 30. I'm going to take this one step at a time. 6 times 5. Okay, so this term times this term with the radicals gives me this term, which I will simplify, my next step, plus, I'm going to say this term times this term, so this becomes 2 square root of 6 times x. Okay, so we multiply these two together, then we multiply these two terms together. And it can get messy, so I encourage you to take as many steps as you need. It's better to take more steps than to make a mistake by trying to condense all your work. Okay, glass of water real quick. Just a moment. Okay, there we go, that's better my throat. All right, so now 2 times 2 is 4 square roots of 30 plus 2 square root of 6x. And 4 square roots of 30, can we break this down? Simplify this? Well, let's see, are there any factors of 30 that are perfect squares? We have 6 times 5. Let me look at all the factors of 30. We have 1 times 30, 2 times 15, 4 times nothing. So 4 is not 5 times 6, so none of these work. So we'll have to leave it at that. These are not like terms. So this is as far as we can go for that one. Now, taking it one step further and multiplying 2 terms by 2 terms. Some people use FOIL method, but I like to just call it distributing when I'm multiplying. This next method, or this next example, will have 2 terms by 2 terms. So let's go ahead and take a look at something like the square root of 2 minus the square root of 3 times the square root of 2 plus the square root of 6. Okay, we'll keep it simple at first. So now we have a lot of terms to multiply. As you recall from before, people would FOIL this, but the way I like to do the problem is think of it. This first term is going to be multiplied with all these successive terms in the next binomial, 2 terms. And then we're going to multiply this term to these 2 terms. And we'll have 4 terms that will then simplify. Okay, so first off, the square root of 2 times the square root of 2, you could take a shortcut as you get more confident with this, but square root of 2 times square root of 2 is just 2. I'm going to write out all my steps in this example though. The square root of 2 times the square root of 6, it's positive out in front, so we have the square root of 2 times the 6. So this term times this term yields this term. And then I move on. When I'm done multiplying this term by all the terms in my next batch, I go on to my next term and multiply by all the terms in my next batch. So here I'm going to multiply the negative square root of 3 times square root of 2. This becomes negative square root of 3 times 2. And then this times this is going to be negative square root of 3 times 6. Okay, now I'm going to go ahead and clean everything up and then simplify as much as I can. Now this just becomes the square root of 4 plus square root of 12 minus the square root of 6 minus the square root of 18. So what we get here is 2 plus here. You can't take the square root of 12 nicely. It's not a perfect root, but I could break this down into square root of 4 times 3, where this part comes out and becomes a 2. Here we have square root of 6. That can't be simplified further, but the 18 can be broken down into 9 times, times looks more like a minus. 9 times 2, where I pull out the 9 out from underneath the square root and becomes a 3. So the 18 contains a perfect square factor, perfect square part. Now my last step is to say 2 plus 2 square roots of 3, which is what this becomes, minus the square root of 6, minus 3 square roots of 2. And I look at this and I try to determine if there's any like terms I combine, and no such luck in this problem. This would be my final answer. We tried, but we did write our radicals as simple as can be. Okay, one more and then we'll move on to divide. Okay, so number 6. One last example. I'll do one with a variable in it. And what I have here is the square root of 2 minus the square root of x and the square root of 6 plus the square root of x. You can have many other combinations that you could build on these basic ideas. You know, you could add more coefficients, more variables, make it get rather messy. But doing the basics here, again, we're going to say this square root times this term gives me, and move a little faster, 2 times 6 is the square root of 12. Now this term times this term, it's going to be a positive, because they're both positive, becomes the square root of 2x. Becomes 2 times the x underneath. Now this term, I'll show that here. Now this term times this term becomes this square root of x times this square root of 6. There's a minus out front because it's a negative times a positive. So we have minus the square root of 6x. And then as you notice with difference of squares in your factoring method, a negative times a positive that are exactly the same become a negative. So minus the square root of x times positive the square root of x becomes minus just the square root of x squared, or x for short, if you want to take that shortcut. Let's see. Next step. Let's simplify each of these. This becomes the square root of 4 times 3, which in the next step I can say is 2 square roots of 3. This is just plus the square root of 2x. We cannot simplify that. There are no pieces inside that are perfect squares, so we just carry that down to our answer. And the same with this square root of 6x. That can't be simplified any further at all as well. Now this, square root of x times square root of x is just x. So I could skip this step if I'm really confident in how the definition is used here, and to say minus x. So altogether I have 2 square roots of 3 plus the square root of 2x. Now these are not like terms. They have to be exactly the same underneath the radical to combine them. So I could just carry them down and write that as my answer. And that is as far as I could go with this problem. So I've multiplied and I've simplified as far as possible, and that is my final answer. Okay, so make sure you practice a good variety of those. Next, I'm going to, before my voice runs out, talk about dividing radicals and rationalizing. So we're going to learn that new term, rationalizing denominators, and it's something that you will hear over and over again. You take more math classes. Okay, so dividing roots, dividing radicals. Some of the same ideas apply, which is make sure that you have the same index number. Okay. So again, you can only divide square roots with the same n. The index. Okay, make sure that you really pay attention to that. You divide the coefficients. Then you divide the radical parts. You can kind of treat the coefficients differently from the radical part, so divide those and then divide the radicals. And then the next step is to rationalize what we call rationalize the denominator. And what that means is get rid of any root in the denominator by multiplying numerator and denominator by the what we're going to do to rationalize, we're going to multiply by a special root or root combination that's called your conjugate. So get rid of any square root in the denominator by multiplying numerator and denominator by conjugate. Okay. So the conjugate is going to be a term we're going to come to when we're going to rationalize the denominator. So the conjugate is going to be different when you only divided by one term versus divided by two terms that have square roots in them. So see the definition coming up. So we'll get to this term conjugate, and that is always associated with rationalizing the denominator. But we're going to start off simple. There's this added step for division that we have to pay attention to. Otherwise, the rules are really the same here. Okay, so here's some examples, and this will get us familiar with the process, and then we can look at rationalizing. So examples, and this will say divide, simplify, and or rationalize. You know, some textbook problems might just say simplify. They expected that you know to do the division or to rationalize. Okay, let's start off with a simple example like the square root of 60 over the square root of 5. Okay, we check this index number is the same as this index number, so we're in good shape. And what we could do is we could just go ahead and say this is the same thing as the square root of 60 divided by 5. We just go ahead and divide our numbers. Those are nicely divisible. And this makes the square root of 12. And now we look at our answer and we see if we could simplify this. We could break this down into 4 times 3, which give me 2 square roots of 3. We've learned how to simplify these type of numbers. So that would be my final answer. Nice, simple, straightforward division problem. 2, let's go ahead and do something like this. 3 square root of 20 divided by 4 square roots of 5. Okay, in this case, same holds. I look at my coefficients, 3 divided by 4, messy, right? I'm not going to touch that, I'm just going to carry that over. But I could do the square root of 20 divided by the square root of 5. So I'm going to rewrite this as 3 over 4, and the top part I'm going to say is the square root of 20 divided by 5. I'm allowed to do that. These are the same index numbers, so I can combine these two radicals and divide this part with this part. So now this becomes 3, the square root of 4 divided by 4. And luckily for me, the square root of 4 is a nice perfect square, and I can say, well, that's just 2. 2 times 3 is 6. And this whole thing becomes 3 times 2 over 4, which become 6 over 4, which become 3 halves. All of that breaks down to 3 halves. Pretty neat. Okay, next up. Let's go ahead and do one with an X. Okay, 3. Got a nice example out here. Let's do square root of, or let's do the cube root of, practice with our cube roots, 80x over the cube root of 10. Perfect. Okay. As before, we want to check to make sure that these index numbers are the same. And they are. So good for us. We could go ahead and say, well, this is the same thing as saying the cube root of 80x divided by 10. Okay, or 80x divided by 10. You could write it this way, especially if you have fractions. And note that they're the same thing. So what this gives me now is the cube root of 8x. And the next part I want to do, that's to simplify this significantly. And lastly, as before, I just want to go ahead and see if there's any perfect cube combinations there. So this will give me, I can break this down into 8 times x, where this is a perfect cube. And my final answer is 2 cube roots of x. And that's it. Okay, now for our very last step, which is to rationalize. So far, I've given you examples where all the square roots just disappear. In the problem, we didn't end up with any answers that had square roots in the denominator. But we're not allowed to have any roots in our denominator in our final answer. So let's go ahead and take a look at a problem and see what rationalization entails. Okay, so to rationalize really means just to make this irrational number into a rational number in the denominator. Okay, so let's see. So rationalizing denominators, you make into rational numbers in the denominator. So you want to make it into a rational number. Okay, so continuing on with this, number 4, we have something like 3 over the square root of 5. And it looks like there's nothing to do with this problem, but the main thing is you can't have roots in denominator. That's just part of a convention we do in algebra. Later on down the road, it's dependent upon your situation. You could leave those numbers like that if you're just doing some lab work or jotting down notes. But we like to, for formal purposes in math, we like to get rid of these square roots and understand how to work with them and make them easier to work with numbers. So what we do is we multiply by the conjugate. So you multiply by your conjugate. And when you have one term in the denominator, you multiply by that root. Root or by combo that gets rid of the root. I'm going to say and or. There's many tricks here. There's a lot of density contained in the statement. So you multiply by that root and or a combo that gets rid of your root used. Okay, when you have two terms, you multiply by the same two terms with a opposite sign between them. I shouldn't say same two terms or a combo to get rid of your roots. Okay, so two terms and one term conjugates are a little different. So that is the main takeaway. There's a few more buried details in there, so I'm just summarizing. And so sometimes when you cut corners, you're not as formal, but just be aware there are straightforward definitions for those. And I'd encourage you, if you really wanted to know more on the details, to go back to those definitions. For our purposes, we're just going to look at one term and two terms, some simple examples. So what I want to do is I want to get rid of this square root of 5. I want to eliminate the square root from the 5. So to do my conjugate here, it's a one-term example. It's the square root of 5, since what I have here, the square root of 5 times the square root of 5, would allow me to get rid of the root and rationalize it to produce a rational number in the denominator. Now I can't just go ahead and multiply this by a number and not this. I have to keep the value exactly the same. I cannot change the value of the fraction. So what I do is I take my 3 square roots of 5 and I multiply by the square root of 5 over the square root of 5. I multiply by the value of 1. So it's like expanding fractions or simplifying fractions, right? You can multiply by the same factor, numerator and denominator, and get the same output. So what I do, I take my conjugate and I multiply by my conjugate. Numerator and denominator. Very important idea. Multiply numerator and denominator by a conjugate. So what do we end up with here? Now, we end up with 3 square roots of 5 over 5. Right. Now I look at my answer as always and see if I can reduce, simplify, do anything else, get rid of any more roots, simplify my roots, but that's as far as I can go, and that's my final answer. At least my final answer has no root, right? No root. That means we're good. All right, let's move on to another example. And 1 or 2 more. I'm going to take a look at my worksheet. This now instead. To rationalize this, I multiply by my conjugate. Which is just the square root of 5. So if I have a coefficient in front, the conjugate is going to be just the square root part. I don't need to multiply by a 3 out in front because all I'm interested in is to get rid of this square root of 5. Eliminate. And the way I can ensure to eliminate this is just by multiplying by that same root of 5, top and bottom, numerator and denominator. So it's like a puzzle. When you're rationalizing, you're really trying to solve the puzzle of what am I going to multiply numerator and denominator by to get rid of that root in the denominator. And that's the ultimate question. So here I'm going to have 6 square root of 3 divided by 3 square root of 5 and multiply by, I see that I can already reduce this. I didn't pick the best problem here, but it'll work. I'm just going to multiply by the square root of 5 over the square root of 5. And what that does is give me 6 square roots of 15 over 3 times 5. And I have 6 square roots of 15 over 15. And I can reduce this to 6 and 15 both share a 3. This becomes 2 square roots of 15 over divide by 3, 5. And that would be my final answer. I've rationalized that. One more example to go over. All right, let's go over 2 terms. Let's say we had a problem where we have 3 over 2 minus the square root of 5. Now the puzzle is, how do I get rid of that square root of 5 when I have 2 terms? I can't just multiply by the square root of 5 square root of 5. It'll get rid of this square root, but it'll bring introduce another square root into the problem right here. So what I need to do is multiply by the conjugate to use the rules for two terms. So I have two terms. My two-term conjugate here will be to multiply by 2 plus the square root of 5. Because I use that idea behind the difference of squares in factoring to note that if I multiply 2 times 2, I get 4. And then when I have opposite sign in between, I'll cancel all my middle terms out, and then I could just multiply by the square root of 5 and the square root of 5 and eliminate the root from the denominator. So let me go ahead and write this out. So my conjugate here is this 2 plus the square root of 5. So I'm going to take 3 over 2 minus the square root of 5, times it by 2 plus the square root of 5, 2 plus the square root of 5. And what I end up with here is, if I go ahead and distribute, I get 6 plus 3 square roots of 5 over 2 times 2, which is 4, 2 times the square root of 5, minus 2 square roots of 5, and then minus the square root of 5 times square root of 5, square root of 25, or just 5. I'm going to kind of condense my steps here. Now what I have is 6 plus 3 over the square root of 5 over, this cancels, and this whole thing just gives me a -1 in the denominator. Okay, 4 minus 5 is -1. This is 0. And now my final answer is this over -1, but to clean it up, if I divide each of these by -1, or if I multiply by -1 over -1, I end up with my final answer of -6 minus 3 square roots of 5. And that is a much cleaner answer. It's rationalized. It has no square roots in the denominator, no roots at all, square roots, cube roots, or any type of roots. So before we leave off, one last comment here, something to explore so you get familiar with conjugates is, if you had the problem 3 over 2 plus the square root of 5, what would be your conjugate? And what would you use instead to rationalize the denominator? In this case, you would have 2 minus the square root of 5. So you would just go ahead and say 3 over 2 plus the square root of 5, and you'd multiply by 2 minus the square root of 5, 2 minus the square root of 5. So I encourage you to go ahead and simplify that and see how it works. So this will have the 2 minus square root of 5 conjugate, whereas this one will have the 2 plus 5 square root of 5 conjugate. Okay, and I think that is it for now. We could get more practice on these, but that's the basic idea. All right, thank you, and we'll see you in the next part.